All right. Hello, everyone. Welcome to the Oxford week of the work of the school. We're going to talk about the strong CP problem. Um, if there are questions in the middle of the lecture, please ask. If they're sort of clarifying questions, I'm just happy to answer them, or I can repeat the questions for the recording for the mic. So it would be good to just make this interactive. So before starting with the details, just a bit of introduction to the topic, and just to calibrate all of us at the same page. Um, so what is the strong CP problem? If you look at the Lagrangian for QCD, written in a certain way, um, this is what the Lagrangian looks like. So just show of hands, how many people have seen this presentation of the Lagrangian and with all the indices being implicit? How many people have uh, not seen this notation? Okay, there was a unitarity violation. The number of hands was not adding up to. So yeah, we should say if there's any questions, you should really stop and ask. It won't be helpful if I talk at you without knowing what the notation is. So this is a notation where very quickly these are 3x3 matrices. These are the Yukawa matrices. Q is the quark doublet written in terms of left-handed Weil fermions. U conjugate and D conjugate are also left-handed Weil fermions. So there's SU2. Yes. Yes. Higgs tilde is Higgs. So in the standard model, there's only one Higgs doublet. So Higgs tilde is just the in SU2 in the SU2 notation. Okay. So if you hmm? Oh yeah, it doesn't. I mean, it doesn't matter. We could define it one way or the other. Yeah. So in general, in supersymmetric theories, for example, in two Higgs doublet models, there would be an H up and H down here. In the standard model, they're the same. There's the same one. It's only one Higgs. So it's a Higgs tilde is just how we are contracting the indices, SU2 indices between the SU2 doublet quark and the Higgs doublet here. One is contracted with an epsilon, and the other is H dagger dotted with the quark. Okay. So the statement of the strong CP problem is that this QCD Lagrangian itself contains two CP violating phases, and we can parameterize them as such. One is a CKM phase, which in one invariant way looks something like this. So it measures the non-commutativity of this matrices YU dagger, matrix YU dagger with matrix YD dagger, and the phase of that object is the CKM phase, and this we've measured to be some order 1 number. There's another invariant combination we could make, which is a combination of this theta angle and the Yukawa couplings, and this we have constrained to be less than 10 to the minus 10. So that's in a nutshell the strong CP problem. There's two phases in the standard model, at least in the strong sector, that you can make out of a Yukawa matrices and this theta angle. One of them we've measured to be non-zero. but the other one we have no evidence for, and it's very, very small. And so why is that the case? Is that something to worry about? Is that a problem or not? Is the whole question about the strong CP problem. Okay. So as you can see, that one of the important roles in the whole game is played by this topological angle, the theta angle, and so that's one novel feature about the strong CP problem. It involves in an intricate way topology and non-perturbative aspects of physics. Okay, so why should we study this problem? Why is this interesting? So the first reason is sort of phenomenological. These theta angles are some of the last renormalizable parameters of the standard model that normalizable. So if you want to really say that we have studied the standard model, and we have, at least even within the framework of the standard model, we've measured all the renormalizable parameters. These include these theta angles, and we would like to understand what is their size, what is their how much they are, and relatedly, if there's something that explains the smallness of the strong of the theta bar angle, the resolutions to these. So one resolution that we're going to talk about in the set of lectures is the axion. They are expected to show up in ongoing experiments. At least optimistically, near future experiments. So this is a structural problem in the standard model, and there are experiments that are ongoing today and over the next decade coming online, which are actually have signals in them that are expected. So if you ask anybody, the next fundamental discovery in particle physics, there's a very good chance their bet would be on something like the axion. Right? So phonologically, it's important for us to understand the physics of these resolutions, because they might be the next experimental discovery. The physics of the theta angle connects with non-perturbative aspects of the standard model, and so there are beautiful quantum field theory objects that come to bear on understanding what the physics of this theta angle is. That we'll spend a little bit of time understanding, and there's still papers being written trying to understand the nature of the strong CP problem, and whether the fundamental way we do QFT somehow undercuts even the existence of the strong CP problem. So it's a subtle and beautiful subject, which there might still be sort of fundamental things to learn from, and also connects with modern developments in formal theory. Formal QFT literature, such as generalized symmetries, non-invertible symmetries, etc. And finally, right here, it connects with so the resolutions, we'll see that for the strong CP problem often involve pristine global symmetries. Some of the more most pristine global symmetries that we've encountered so far. So this has direct connection with aspects in quantum gravity, where people now um, strongly believe that in theories of quantum gravity we can't have global symmetries, and so there's a whole program of thinking about what QFTs can be UV completed into theories of quantum gravity. One of the most robust things people think is that global symmetries are very hard to accommodate in quantum gravity, but to what extent they're violated is not clear. Some of the most pristine global symmetries that we encounter actually come up in the context of solutions of the strong CP problem. And so this is a prime realistic, prime phenomenological example to apply some of these considerations from quantum gravity into. So again, often this is in the context of axion physics, but not just there. So again, we will touch upon at least some of these aspects. So as you can see, that the strong CP problem has been around for a while, but it's both experimentally and theoretically, it's very relevant today. There's new developments that people are still understanding in formal QFT, in connecting QFT with theories of string theory or quantum gravity that have relevance for theories solving the strong CP problem. But at the same time, there's a vast experimental program, both on tabletop experiments, cosmology, astrophysics, that relates to the solution of the strong CP problem. Okay, so this is why I would like to at least understand some of the problems related to the strong CP problem. Let me give you some references, general references. I'll probably give you slightly more specific references when we are dealing with a specific topic. So there's a large set of TASI lectures, recent and less recent, which are worth reading. The more recent ones, there's a set of TASI lectures by Matt Rees. There's a set of TASI lectures by Anson Hook. Matt's lectures are more emphasizing this last aspect that I mentioned, global symmetries in theories of quantum gravity. Anson's lectures are more related to the phenomenological aspects of strong CP problem. Other places we'll draw from are David Tong's lectures on gauge theory. These are very nice lectures on modern aspects of gauge theory. If you haven't seen them, I recommend them to you in their generality. We'll pick up some bits and pieces from various parts. Some more classic references are, of course, we'll use some aspects of symmetry by Coleman. We'll talk about another reference which is useful when we talk about the chiral Lagrangian is weak interactions by Georgi. And finally, there's a classic paper that we'll try and follow when we discuss the chiral Lagrangian, which is Large and Chiral Dynamics by Witten. So this is a partial list of references. We'll add more references as we go along. Okay, so now I need to erase. So here's a rough plan of what we're going to do. We're going to spend some time just talking about the physics of the theta angle. And we're going to use a particularly simple system, which is the quantum pendulum. To describe this physics. The physics of the theta angle can be really subtle. And there's again there's still some debate in the literature about how to think about the theta angle. And this particularly simple system has all the subtleties that we encounter in the theta angle in a theory like QCD. And so it's a very nice example to study, which we can do in gory detail. And we think we know what the quantum pendulum should do, so we can actually elucidate all the subtleties that arise. Then we'd talk about the theta angle in the standard model. And really see how does the strong CP problem in detail look like in the standard model, and how does the theta dependence look like, both in terms of thinking about the standard model perturbatively at high energies in terms of QCD, but also at lower energies where QCD is strongly coupled, but then we use chiral Lagrangian to describe the physics. And then we'll move on to solutions of the strong CP problem. There's a class of solutions which are based on discrete symmetries, and I'd like to tell you about how to think about these discrete symmetries in a slightly more modern language, which connects with some of these aspects of generalized symmetries that I mentioned. We won't have time to flesh out the entire field there, but at least make a connection with how generalized symmetries show up in thinking about these discrete symmetries in a modern way. And there's a class of solutions I just called axions, which is a second class solutions to the strong CP problem that that is both phenomenologically as well as theoretically interesting. Okay. So this is the plan. Before we jump into the actual nitty gritty, any questions so far? Okay, so let's begin talking about the quantum pendulum. So we're imagining a pendulum, let's say supported by a rigid rod, so that it can rotate all the way around. And the pendulum is dictated by an angle, let's say some angle alpha. And so that's the degree of freedom, alpha, which is the degree of freedom, which is, say, goes from, say, 0 to 2 pi. In other guises, this problem is also known as particle on a circle, because this part, if you think about this pendulum bob, that is constrained to move on a circle. So you'll often see this system described as a particle on a circle. Okay, and classically, I hope everybody's seen how the pendulum goes. Quantum mechanically, we can write the Lagrangian for the system, which looks something like this. So there's a theta term that's already present in the let me first stick with alpha. There's a theta term that's already present in the quantum pendulum that is not familiar from the classical state. One way we can think about motivating this is to imagine the particle at the end of the pendulum is charged, and imagine some amount of magnetic flux going through this circle. So imagine there's a solenoid in the middle with some magnetic field pointing out, and there's a charged particle. So what this theta angle is exactly is in this analogy, it would be the flux of magnetic field through the circle. But as we'll see, maybe towards the end today or maybe early tomorrow, that there's many physical systems very close to the QCD theta angle that are actually described by this quantum pendulum. So this interpretation is not the only interpretation I want to keep in mind, but just to motivate why are we studying this Lagrangian, this would be this theta would be associated with the Aronoff-Bohm phase of a charged particle going around a solenoid. Okay. And we'll see that this theta actually has physical effects in the context of the quantum mechanics of the pendulum. So we'll see again and again that it's actually more convenient, instead of thinking about a variable that's valued in 0 to 2 pi, where now it has a jump at 2 pi. It's much more convenient to work in a variable which is defined minus infinity to infinity. So that's like unfolding the circle. But now we have to add this information that actually we are on the circle. So when we go from a 2 pi distance on this variable q, then we come back to the same point. So we're parameterizing, instead of this jumping variable, we're parameterizing our circle with on a real line, but we add with an added identification that q is the same as q plus 2 pi. Okay. By the way, I could put units. There could be moment of inertias here and so on. I'm just setting things to 1 just for simplicity. We won't so that we have less to write, but we can add units if we wish. Okay, so this is the first conceptually interesting thing that's happened, that we've now introduced gauge invariance in our theory. Okay, so this is not saying that there's a symmetry. This is saying that our system is a circle, and we are parameterizing the circle with this variable, which is an infinite line. So this only makes sense if we identify q with q plus 2 pi. Okay, so this is an identification or a gauge redundancy. Often we use the word gauge symmetry, but actually gauge symmetries are nothing but redundancies in our systems. Okay, and in particular here in this case, as we'll see, this transformation q to q plus 2 pi is the analog of what is called a large gauge transformation. Okay, so this is an important conceptual point to that gauge symmetries are redundancies. They're just introduced. So because we said q is a more convenient variable to work with rather than this alpha variable. And if you want to work with this variable and still want to retain the property that we are on a circle, we have to identify this q with q plus 2 pi, and that is the notion of gauge transformation. Okay. So let's first look at very quickly the Hamiltonian for the system and see that the theta angle actually does have physical effects. Actually, before that, we can actually construct the classical equations of motion. So the classical equations of motion of this Lagrangian look like this. So if this term, theta alpha dot, is a total derivative in the Lagrangian. This is just d dt of alpha. And the total derivative in the Lagrangian doesn't affect equations of motion. So classical equations of motion don't actually see theta. This is the whole point where in classical mechanics, we never actually wrote this theta down. So first of all, we should be suspicious whether this theta shows up in our physics system at all, because the classical equations of motion don't seem to know anything about it. Okay, and indeed, quantum mechanically it does show up, which is the whole point of its subtlety. So if we construct the momentum operator, the momentum operator looks like, so let me be careful at least about the 2 pi's. The momentum operator looks like this. And so we can construct the Hamiltonian just using canonical formalism. We get something like this. So the Hamiltonian does have theta dependence, and we can solve for, say, let's say the spectrum of this theory and see what it looks like. So we can solve the time-independent Schrodinger equation. Notice, by the way, that the momentum has a funky definition. It's not q dot but q dot plus theta, but really this is the momentum which has canonical quantization with the position operator. So momentum really, in position space, the momentum operator is still given by this. And so we can write down the Schrodinger equation. And then figure out what energy eigenvalues do we get. So this equation has the form of what is called a Matthews equation, and the solutions are special function called Matthew function, which are similar in spirit to sines and cosines. So for example, this is easy. This equation is easy to solve. Let's do it in a limit where our parameter v0 equals 0. So there's no potential. So it's you could say it's a pendulum in space, and we'll get the solution to this equation. Then would be simply the familiar plane waves, but then times this factor e to the I theta q. And the energy for each of these, energy for the k is defined as energy is k squared over 2. Yes, question. So yeah, speak up, please. What? Oh yes, sorry. So this is just this. Yeah, thank you. And then this. Yeah, p squared over 2. This is the p squared over 2 mps from the Schrodinger equation. Okay, so I'm going through this slightly quickly because just to set up at least our expectation for what the theta dependence of this spectrum would be. Our Lagrangian had a theta which was a total derivative. It didn't show up in the equations of motion, but it does show up in the Hamiltonian. We can solve the Schrodinger equation, and then now let's try to find out what the energy eigenvalues would look like. Oops. So as usual, the way we get the energy eigenvalues is by imposing boundary conditions on our wave function. So let's impose what would seem natural periodic boundary conditions, which is psi of 2 pi equals psi of 0. Okay, and we'll have much more to say about boundary conditions and the periodicity of the boundary conditions subsequently. But let's do something which seems natural. Let's impose periodic boundary conditions. So when you impose periodic boundary conditions, one of the solutions can be chosen to satisfy the boundary condition, and the other one will have to be thrown away because that will not satisfy the boundary. For example, we could choose k minus k plus theta over 2 pi to be equal to an integer. Okay, then so that solution then that will ensure that psi is periodic. The other solution will be thrown away, and so the our energy eigenvalues, which was half k squared, are now half n minus theta over 2 pi squared. So we explicitly see that the energy eigenvalues are theta dependent. Theta has a physical manifestation, and instead of getting integer quantized energy eigenvalues that we are familiar from a periodic particle in a periodic box, we actually get something that's shifted by theta. Okay, and this kind of behavior is typical of the theta angle in various theories. The whole point of studying this quantum mechanical theory is that it actually is a relevant analogy for theta that appears almost anywhere in physics, which is gauge theory, condensed matter systems, lower dimensional systems. You have it, and it also when we'll talk about the axion, you'll see that the theta is actually also a reasonable stand-in for the axion itself. But when we'll get there, we'll make that more precise. So let's do one quick thing. Let's plot what the spectrum looks like as a function of theta. So theta is a parameter near Lagrangian, so it's not actually a variable, but I just want to look at the spectrum of the theory as a function of theta. So theta equals 0, I have the usual particle in a box energies, so 1, 2, 1, 4, 9 would be my energy levels at theta equals 0. And the dependence on a given energy level on theta is just quadratic. So it will just be, if I plot, for example, the n equals 0 level, then it would be something like some quadratic function like this. Okay, and similarly, if I plot the n equals 1 level, then it's a little bit of tricky drawing, so I want to get it right. So let's say theta is 2 pi here. So if you look at n equals 1, then it has its minimum at theta equals 2 pi. And so it looks something like the same parabola. And similarly, this level at n equals 2 will have its minimum at theta equals 4 pi. And so it'll again be a shifted parabola like this. Okay, the drawing is horrible, but hopefully you can see what's going on. So at any given value of theta, we have the spectrum. At theta equals 0, it's the usual spectrum of n squared. At any other theta, the spectrum is deviated from that spectrum. But you see, when theta goes to theta plus 2 pi, this whole pattern 0, 1, 4, 9 is repeated again. So what was the first excited state at theta equals 0 now becomes the ground state at theta equals 2 pi. The n equals 2 state becomes n equals 1 at theta equals 2 pi, and so on. Okay, so as theta goes to theta plus 2 pi, we have n goes to a state n effectively goes to state n minus 1. So the spectrum of the theory is actually the same at theta equals 0 and theta equals 2 pi. But if you follow one particular branch of the solution, the um, the one particular branch of the solution changes, of course, as theta happens. So this is again a very typical thing that happens as a function of these theta angles. The theory is periodic with respect to theta going to theta plus 2 pi. But the spectrum, each individual state in your spectrum actually changes as a function of theta. So if you follow this state as a function of theta, it's not periodic at all. It never comes back to itself, but the spectrum comes back to itself. So this idea is called spectral flow. And again, it's repeated in almost all many examples, almost all examples that involve a theta angle. Okay. It's also possible um, to solve the Matthew equation, which I've raised now. So let me write it again. So in the limit of theta equals 0, we can actually solve the Matthew equation exactly. And this is um, this is the problem. This is the first exercise for you to do, which is to solve this equation. So the relevant terms you could look up is Matthew characteristic numbers. That will tell you the Matthew functions are the eigenstates of this equation, and Matthew characteristic numbers will give you the energy eigenvalues. And so what you can compare is that look at the spectrum for energy much bigger than V0 and energy much less than V0. And for energy much bigger than V0, you should get back what we just found, because for very high energy states, the potential is irrelevant. So we should get back results close to the particle in a circle. For energy much less than V0, you should get back spectra which resemble the harmonic oscillator spectrum, because you're sitting at the bottom of a cosine potential. That should look like a quadratic potential to that low energy. So you should see when you look at the eigen values for this exact equation, it's a nice thing to see that it actually interpolates between these two limits that you could that you can approximate the solutions by, and see where that turnover is in terms of which energies for which energies the turnover between the harmonic oscillator-like states and the free particle on a circle-like states. Good. Any questions? Yes. Um, yeah, so you can have instability. So depending on what problem we're this kind of problem can appear many places, right? The cosine potential. Depending on what problem you're talking about, there are instabilities in Matthew equations, which go by the name of Floquet theory. In this case, what we'd find is if you impose the conditions for finding eigenstates, which is periodicity of the wave function, these will all have real energy eigenvalues as you'd expect from a quantum mechanics problem. But there are instabilities in the Matthew equation, of course, in different problems. Yes, question. Yes, there is size missing all over the place. Thank you. Thank you. Okay. Um, so okay. So what we established is that theta would affect the physics at the quantum level, and we can in fact look at the theta dependence in the simple system of a particle and a particle without a potential. But what would be interesting and connect much closely to the case of the gauge theory is to look at the case where uh, both theta is present as well as we have a potential. Okay, and the one simple way to deal with the problem there is to use instanton semi-classical methods, and we will meet instantons and the instantons and their interaction with the theta angle. So to solve the problem in the presence of both theta as well as the potential, we'll go to semi-classical method and talk about instantons and the path integral. So if we go back to our to the basis alpha, we could ask questions which are we can ask quantum mechanical questions which are what is the transition amplitude for the particle starts at some particular angle. If I put the particle at some particular angle in my system at some time, initial time ti, what is the amplitude to find the particle at some final alpha at some final time tf? And Feynman taught us that we evaluate this using, you can evaluate this using path integrals, where we do a path integral over all possible paths connecting alpha I to alpha f. So the boundary conditions are alpha ti equals alpha I, alpha tf equals alpha f, and we do all paths which are weighted by e to the I the action. So that's the prescription, the path integral prescription of um, finding this matrix element. Pictorially, let's draw it how it looks like. So we can draw the circle at time ti and the circle at time tf. And so let's say this is some point alpha I, and this is some point alpha f on the circle. And so when we're doing the path integral, we're actually doing all paths on the cylinder, the time direction and the circle in a quantum mechanical direction. So there's some paths which look like this, and fluctuations around these paths. There's paths which look like they're winding around that also are included in the quantum mechanical path integral. The paths which look like they're winding around, but then they double back out. So there's all paths you can imagine on the cylinder contribute to this sum over paths in the quantum mechanical integral. Okay. And again, as before, it's actually more convenient to work instead of these angular variables that are valued in 0 to 2 pi. It's more convenient to work in the variable q. You can imagine that, let's say our angle was defined 0 here and 2 pi around. Any path that crosses that international date line has to jump, and so that's an unphysical jump in a smooth path, just because you're jumping coordinates. So as you cross 2 pi, you go back to 0 artificially. So It's actually much more convenient to work with this picture, but then in the Q basis. So in the Q basis, we'll have at time ti, we'll unroll the circle. To include gauge copies of our original circle, which was defined on one domain. And so now again, gauge transformations take us from any point on this line to 2 pi across this line. Okay, so all these points are gauge identified with each other. All we're doing is to rewriting the circle or the cylinder in an unfurled coordinate, so we have to identify these strips. So the same question now includes the sum over gauge copies as well. So if our initial position was, let's say here, this was some alpha I, and this was alpha f, then there's a path that goes like this. There's also a path that goes to the gauge copy of the same final point. That this extra path corresponds to winding around the cylinder one time and ending up at the point on the cylinder. And so now the sum over paths, the path integral is sum over all these paths. In principle, it's also a sum over all the initial states. We'll talk about it in a second. But the crucial thing to now understand is that now this strip is well defined. Q goes from -infinity to infinity. But now you have to sum over. So each path is smooth. You can evaluate its action, but you have to sum over the final images of your final state point. Okay. And so again, this is mathematically equivalent to doing what we were doing here. The question we asked was to sum over all paths on a cylinder. The answer is, in this basis, summing over all images of the final final state. So let's see what that looks like in terms of the path integral. Let's pick certain values just for simplicity. Let's pick 0 and 0 for the alpha. So we're asking for this matrix element. And what we find is that we can write it as an integral over q e to the I L dt. But now we have to sum over all possible values of q. So q going from 0 to 0, q going from 0 to 2 pi. So this would actually be boundary conditions q equals 0 to q equals 2 pi n, and we'll sum over n. Okay. Let's separate out the theta dependence in the L. So oh, good. Yeah. Right. Good. So I said I'll set. So you're right. In general, we'd have sum over the initial state as well as the sum over the final state. The sum over the initial state will give us m copies of the same thing, and so this will actually give you an infinity because it's just m copies of the same thing. So you have to gauge fix. So what you do is let's say, so this is the same, by the way, the same infinity you get in Faddeev-Popov when you do the quantization of gauge theory. So you gauge fix. Let's gauge fix to the first thing to be one position 0. Then each n is a physical winding number of the path integral. So this n is actually a physical thing you're summing over. Thanks. Yeah. So let's explicitly write out the theta dependence. So let's say L0 is the Lagrangian without the theta term, and I'm going to explicitly separate out the theta term. Um, like so. So now notice this, the fact that this is a total derivative is important. This integral only depends on the final and initial values of q. This integral is just equal to delta, this delta q times theta over 2 pi. It does not depend on anything. It doesn't depend on the rest of Lagrangian. It doesn't depend upon what the path is doing on its way from initial to final. This is the manifestation of the fact this theta is a topological angle. It only depends on the initial and final condition. So this thing just becomes delta q between in each of these winding sectors is just n. So this just becomes e to the I n theta. And you can see that now it doesn't depend on any details of the path, so I can actually take out this n theta out of this path integral. So this gives us another perspective on what the theta angle is doing. It's telling us that when we're doing the path integral in a cylinder, we have a bunch of winding sectors. So all our paths break up into paths labeled by n, how many times they wind around the cylinder. Each of the winding path is weighted by e to the I n theta, where n is the number of times the path winds around. The net number of times the path winds around the circle from time t equals ti to t equals tf. And this is not unexpected if you think about our initial analogy of the Aronoff-Bohm phase, where we say if a charged particle travels around a solenoid n number of times, it picks up an Aronoff-Bohm phase, which is proportional to the flux carried by the solenoid, and times the winding number. Okay, so this is another perspective where instead of thinking about instead of thinking about the theta angle as part of the Lagrangian, we can not include the theta angle in the Lagrangian at all, but posit that for each winding number n, we weight the path integral factor by e to the I n theta. Okay, so you'll sometimes see presentations of the path integral in a way where the theta angle doesn't appear anywhere except to posit this dependence on the path integral. But as we saw, this is exactly equivalent to having it in the Lagrangian. Okay, so different presentations might put the theta angle in the partition function or in the path integral in this way, or in the Lagrangian from the outset. But you should see that that's just a way of describing the same physics at the end. Okay. So now what we'd want to do is to use this to evaluate this path integral in the semi-classical approximation. But before we do so, we'll take a little bit of a detour into a system which is very, very similar, but in a subtle way, it's slightly different, and that difference and similarity would help hopefully sharpen the nature of the theta vacuum. Okay, so before we go on to the detour, are there any questions? So let's consider a system which is somewhat closely related to this particle on a circle system we've been talking about, and highlight the differences. So Lagrangian for the system is This is a system of a 1D lattice, if you will. So there's a particle that's traveling in a periodic potential. But the crucial difference from the case we're studying is that the system is defined on an infinite straight line. So there's actually physically distinct points, 0, 2 pi, 4 pi. So this is not the particle on a circle precisely because we do not yet now have a gauge symmetry that relates these points with each other. Okay, and so as you might imagine, if you really had a 1D lattice, you could choose one point and put a defect there. On a circle, you don't have a choice of picking one. If you put a defect on the circle, it appears in every copy of the when you unroll the strip. Here, if you put a defect in one place, you're free to do so. There's nothing relating these different. So that's the crucial yet subtle difference between the two systems, and we'll see how the path integral can be related and what the differences between the path integral is. We could add a theta term here, by the way. The theta term here does not actually have the same kind of effect. Okay, so we could add a theta term, but just for simplicity, let's not do that because it certainly won't have the same effect as the theta term there. There's no notion of winding paths for a particle on a 1D line. Okay. The classical states of this Lagrangian would have n different n possible sites. Let's say there's a would be labeled by some integer, so the particle could be sitting in any one of these potential wells. And so the classical ground states would be a large degenerate set of states, which are particles sitting at one of these one of the minimum points. Okay, but quantum mechanically, this is impossible. Maybe one of you can tell me why. So classically, the statement is classically a large degeneracy of states, ground states, labeled by some integer which well you're sitting in. And my claim is this is impossible quantum mechanically. Does anyone want to hazard a guess or explanation for why that is the case? Yes. Okay. Yeah. So the proposed resolution is that as long as these states can interact with each other, the levels would actually split from each other. Yeah. So this is correct. Another way to say the same thing is you can imagine just a simpler system of a double well, where again classically you would say there's a state that's localized here and the state that's localized here, and you might ask if there's a degeneracy of the two ground states. So let's call this state L and a state localized here R. But what you find is that these linear combinations are the actual energy eigenstates, and the symmetric combination, so the ground state is this, and the excited state is the antisymmetric combination. So this is the ground state, size 0. And the splitting between the ground state and the excited energy state is related to the tunneling amplitude. So the interaction between these two wave functions. Okay, so indeed in quantum mechanics, in 1D quantum mechanics, particle mechanics, there's always a unique ground state. So we can't actually have a degeneracy of ground states in 1D particle mechanics, and so we should find that actually this classical degeneracy of states is lifted by effects that are related to tunneling under the barrier, and it's exactly those effects that we want to elucidate using the path integral. Okay. So yeah, so let me tell you the answer, and then we'll work towards the answer using the path integral. Uh, this is a classic problem in condensed matter physics, particle traveling in a 1D potential. The energy eigenstates are given by what are called block waves, and so the energy splits up into a band of states labeled by some parameter, and so we'll find when we treat this problem semi-classically, we'll find that band of states which are linear combination, which are similar to this. Instead of two states now, there's a large number of linear combinations you can take of symmetric and antisymmetric combinations of various localized states, and those would form the band of energy eigenstates that we'll find. Okay. So if you had in particular, instead of an infinite periodic potential, if you had a finite number of sites, you would get a corresponding finite number of states in the band. For an infinitely long periodic potential, you get a continuous band of states. And we'll see how that plays around, and that'll and I promise you all this detour is worth it. It will help us understand the theta vacuum in a very nice way, hopefully today. Okay, so the way we want to find the lower lying energy spectrum of that system is to use the following fact. If you evaluate a path integral, if you evaluate this matrix element for going from some initial position to some final position using this, but the matrix element of this operator, at large times, this projects out the ground state of the system. You can see that any term which is coming from higher energy states will be more exponentially suppressed. So in the limit t goes to infinity, this will be dominated by plus corrections which are further exponentially suppressed. So this is one way that we can extract information about the ground state of the system to evaluate this matrix element, and this matrix element is nothing but doing a Euclidean path integral. And so Euclidean path integrals are path integrals done in Euclidean time. T goes to I times t, and there you can see that why that is the case here. Usually time evolution operator would be e to the I ht, but if we do a imaginary time evolution, that gives us e to the minus ht. And so what we want to do to prepare this state is to do the Euclidean version of the path integral. And in general, sort of it's almost a rule that Euclidean path integrals are useful because they let us prepare states. Euclidean path integrals are, the whole point is that help us in state preparation. In this case, we are preparing the ground state when we're doing a Euclidean path integral from, say, some xi at minus t by 2 to at t by 2. And so the leading behavior of this Euclidean path integral will tell us what the low-lying spectrum is. So what we're going to do is to evaluate this Euclidean path integral using semi-classics. And we'll meet our friend instantons there, which which you'll meet everywhere in this course, and also meet them in when Ed's talking about vacuum decay. So the idea of the semi-classical evaluating these exponential integrals using semi-classics is that these exponential integrals are dominated by places where that integrand is stationary, and around what we can do is we can find places where that integrand is stationary. So the Euclidean action, this quantity, we can find places that Euclidean action is stationary, and we can do small fluctuations about those stationary points, and so our integral is going to be given by Euclidean action of the stationary points times fluctuation. So the first thing is to find stationary points of the Euclidean action. Stationary point of the Euclidean action are just solutions of the Euclidean equations of motion, which are, in our case, these. So this is the equation of motion for the particle, but with an inverted potential. Remember, if you actually wrote out the classical equation of motion for the particle, you'd find x double dot is minus dv dx. If you're trying to find Euclidean solutions to the Euclidean equation of motion, you find that it's these are the equations of motion with an inverted potential. So in other words, the potential now looks like this. Okay. Yeah, let's fix something just to be able to draw pictures. Let's say xi is 0, and xf is some other point. Let's say 2 k to j pi. Okay, so we're going between one of the minima of the classical potential to another minimum of the classical potential. So a stationary point, a stationary solution of the Euclidean action would be classical solutions on this inverted potential. So what are the trajectories, classical trajectories on the inverted potential? So depending on the boundary conditions, some of the trajectories would be just sitting on top of the potential forever. That's a classical solution. Another trajectory that is a classical solution for this potential is to go between these two maxima. So the particle starts at the top of the hill and ends up at the top of the other hill. In time, that solution looks something like so. For a long time, the particle sits at the top of the hill here at 0. And it goes over and then sits at a long time at the top of the other hill at 2 pi. Okay, so for the inverted potential, which are going to be our stationary points around which we'll expand that our Euclidean path integral, the stationary points give us different possible trajectories depending on the boundary conditions we impose on the path integral. All classical trajectories are stationary points of the Euclidean action around which we want to expand our path integral. Okay. How many people have seen this before? Just show of hands. Okay, there's a fair number of you haven't. So please do ask questions if you haven't seen something before, just to serve to slow me down if things are unfamiliar. So let's do it here. So we can any given trajectory. Remember, we're integrating over all possible trajectories here. Any given trajectory, what we want to do is to say uh, is one of these classical trajectories, which are solutions to the Euclidean equation of motion, plus some fluctuations. So um, so let's call these classical solutions x bar of t. So these are prescribed functions, which look something like, I should really label it as x now that I'm talking about the periodic potential. Um, so let's label x bar of t the classical solution, which is some prescribed function of time, which is a solution to the classical equation of motion. And if you're given a potential, we can actually go ahead and solve that differential equation and find what the shape of this function looks like. So it's some prescribed function, and we're saying that we're going to expand around all possible classical solutions plus small fluctuations around, put a delta here if you wish, where now this delta of x of t is not allowed to go between 0 and 2 pi. It's supposed to live close to the, it's supposed to be a small fluctuation around these trajectories, okay? So our path integral is dominated by trajectories like this, which are some classical trajectories plus small fluctuations. And we can expand our Euclidean action as the action of the classical trajectories, so S classical, plus plus quadratic fluctuations in the small parameters, in the small fluctuations, okay? There's no linear, when you do the Taylor expansion of this functional, there's no linear term because the linear term is 0 by the definition of the fact that x bar is an equation of motion. So partial s, partial x bar squared is just, is 0. The variation of the action with respect to x at equations of motion vanishes. So again, this is a somewhat standard thing where when you want to evaluate an action, you evaluate it, whenever you're evaluating an action, often we're evaluating around the trivial solution, s equals 0, so we just, when we're doing phi to the fourth theory, we're doing phi to the d phi squared plus phi squared plus phi to the fourth as interactions which are treated perturbatively. So we're always evaluating fluctuations which are small and can be treated in perturbation theory around some classical saddle point of the path integral. Okay. Okay, so let's write out our partition function again, which was, let's give it a letter, let's call this z. The Euclidean partition function is this. So z is going to be going to look like this now, where what I've done is to say that we're going to take this full integral of over all paths and expand it around stationary points of of S. For each stationary point, we pick up the e to the minus s classical x bar of t, and the path integral then becomes just fluctuations. So these are delta x's, just these are small. So here x's are supposed to be small fluctuations, and so it's the classical path plus small fluctuations around the classical path that give us the path integral. Okay, and so we can expand the potential in the quadratic order for small fluctuations, and then there'll be higher order terms like x to the fourth, x to the sixth, and so on, and we can use perturbation theory to do this path integral for the fluctuations. Okay, so so all that formalism just to say that what we want to do is to extract large time behavior of this partition function. The large time behavior of this partition function will give us the spectrum of the theory, the low-lying states of the theory. What we would like to do is to use these semi-classical methods to extract all the dependence on these classical paths and then fluctuations around that path to extract the information. And these classical paths we'll see in a second, would be analogous to what we call instantons. Okay? Question? These are delta x's, yeah. So, sorry, first of all, this should be a path integral here. Writing a bit too quickly. So these are, if we want to keep this notation, the delta x is the fluctuation. This is now the path integral is now over the all the paths which are fluctuations around the classical path. Okay, so let's draw a picture again. So now we have so we have this periodic potential where the particle is starting at x equals 0 and it's ending up at x equals j. What we're saying is that these dashed lines show where the minimum of the potential is, and so the particle goes to these points by paths which are dominantly paths like this plus small fluctuation. So what does that path look like in this context? It would look like something like this plus small fluctuations about these paths. And you can go here. Let's not do that. And then come back here. So all of these paths which spend the long time at the minimum of the potential, all of these are, remember, the minimum of the potential we had, and then tunnel to another minimum, and then spend a long time. All of these paths are stationary paths of the Euclidean action. And the path integral that we want to compute is dominated by, we have to sum over all paths, but in the semi-classical approximation, it's dominated by these paths plus small fluctuations around these paths. So and so in that approximation, we can evaluate what these paths look like, what the path integral looks like. Now with a specific boundary condition. So this semi-classical path that we just described from q equals 0 to 2 pi, this solution is called an instanton. It's called an instanton because it's localized in time, so it's the same the same notion of instantons we'll encounter in field theory, where these field configurations are localized in time as well as maybe in space. But in this case, we just have a time coordinate, and these are localized in time. So it stays at zero at for a long time, and it stays at 2 pi for a long time, and the transition happens relatively quickly. And the width, the time width of this, the profile of this function depends on what the potential is. So it's relatively easy to calculate. It's the classical trajectory where you start with a very tiny, with zero velocity here, and you transition this and end up at zero velocity here. So you spend most of your time at the top of the two hills, and a very quick time transitioning between the two. Okay, so these are indeed instanton solutions. So let's rephrase what we've just said here. What we've said here is that the path integral that we want to compute is all paths between these 2 points. It's dominated by fluctuations around a number of instanton or anti-instanton solutions. Anytime this jump happens, that's an instanton solution. Anytime you go back this way, that's an anti-instanton solution. The opposite of this looks like this. So the Euclidean path integral can be evaluated as sum over instantons and anti-instantons, all spread out in all possible ways such that these boundary conditions are satisfied. So our Euclidean path integral becomes a sum over n and n bar, where there's n instantons and n anti-instantons. So that is some path like this. This would be 1, 2, 3, n equals 3, n bar equals 1 path. And so we sum over n and n bar. Each n bar gives us one particular stationary point of the integral. This is a classical, this is an equation of, this is a trajectory that's a solution to the Euclidean equation of motion. So it's a stationary point of the Euclidean action. And so we want to consider paths like this and fluctuations around that. So we would get something like this for the position of these instantons and anti-instantons. We would get an integral over their positions. In order of their appearance. So you can take an instanton, you could go back, or you could go further. So you can sprinkle instanton and anti-instantons any possible way, with obviously the constraint that you start at the given prescribed initial condition and you end up at the prescribed final condition. So we're summing out all possible ways to do that. And we'll get an integral over the position, the time coordinate of each of them. And we also get n times the action of each of the instantons. So if one instanton action is, if one action of the one instanton is e to the minus s classical, we get n plus n bar copies of that. The action for the instanton and anti-instanton are the same. Just trying to put all the pieces together. And then we get this fluctuation determinant, this path integral. So let me just Let me call this z tilde for now, and for lack of a better. I'm shortcutting a bit of the formalism, so hopefully uh, the result will be sensible. Yeah, so this.